All right. Good morning, everybody. Welcome back. So for today, let's continue where we left off on Monday and advance throughout the next chapter as well. So we need to have a serious conversation, and we are going to do that today. I will spread this throughout the lecture. Okay. So let's go. Guys, we gotta keep going. We gotta keep going. We got to a point that it's almost at the end. You need to give everything. And it's the final sprint right now. All right. So let's see here, do a quick recap where we left off. Okay. So on Monday, I showed you some periodic properties, starting with radius. And radius is the property that will give you a guidance to the other two periodic properties that I'm going to show you here. So first, trend for the radius, when we analyze the groups from top to bottom, there will be an increase in the atomic radius because we are adding extra shells as we move from top to the bottom of a group. And the radius will increase as well from right to left because we are decreasing the charge and adding more electrons, okay? If an element loses electrons, the radius will decrease. Now we have less electrons and the same nuclear charge. Therefore, the nucleus can attract with more intensity the electrons, shrinking the radius, and vice versa. If the element gains electrons, the radius increases. So now electrons are being added. The nucleus has to divide its attention to more electrons. It cannot pull with a lot of intensity, causing an increase in the radius. We briefly talked about ionization energy. The definition of ionization energy is the energy needed to remove one electron from an isolated element in the gas state. Higher the energy needed, higher the ionization energy. Small elements, they need a higher energy to remove the electrons because they are strongly attached to the nucleus, and vice versa. If we have a large element, it's easier to pop one electron out because the interaction is weak. Across the group from bottom to top, there is an increase in the ionization energy. And across the period from left to right, there is an increase in the ionization energy as well. Okay? The first ionization energy is defined as the energy to remove the first electron. The second ionization energy to remove the second electron, and so on. Okay? Usually there is an increase from the first to the second, to the third, to the fourth ionization energy. Okay, so for today, what's left is to talk about electron affinity. Electron affinity is basically the opposite from ionization energy. It is defined as the energy released when an isolated atom in its gas state gains an electron. So we are going to start with a neutral isolated atom, provide one electron to this atom, it becomes negative and will release energy. Again, we will basically determine the trend of electron affinity using what happens with the radius. So let me switch to my other screen to make some notes. Okay, so let's first start analyzing what happens across the group. Okay, so we know that from top to bottom across the group, we have an increase in the radius. Okay, so let's represent here a nucleus with a positive charge and the very last electron. And moving across the group, we are going to increase the radius. Okay, very good. So electron affinity, we are going to provide an electron to the element. This electron has to be held tightly, and in exchange, the element will release energy. So if we have a small atom, when we add an extra electron, because the distance is very short between nucleus and electron, this atom is capable of holding really tight to the extra electron. On the other hand, if we have a large atom, an extra electron added, it's going to mean extra work. It's far from the nucleus. It cannot hold too tightly to this electron. That means moving from bottom to top across a group, there is increase in the electron affinity. Okay, smaller atoms can hold tighter to an extra electron. That means high electron affinity. Now let's analyze the trend across the period. So that's going to be the second part of our analysis, and we are going to look across the period. Moving from left to right across the period, there is a decrease in the radius. So let's move from the very left to the very right across the group. And the result is that the atoms will shrink. And here's the same idea. Smaller atoms, they can hold tighter to the extra electron, making the system stable. If the radius is large, the attraction, the interaction between the nucleus and the extra electron will be weak, reflecting in a lower electron affinity. So therefore, the electron affinity will increase across a period, moving from left to the right. Okay, so keep that in mind. Small atoms, they can attract with more intensity, with higher intensity, the electrons compared to large atoms. Therefore, if we have a chemical bond where electrons are being shared, small atoms will pull those electrons stronger. Okay, keep that in mind because this is going to be important for the next chapter. All right. Okay. So with that being said, that's the end of the periodic trends. And I showed you three properties that change across the periodic table. First one, radius. Second one, ionization energy. And third one, electron affinity. You must understand clearly the trend for the radius, and the other two, ionization energy and electron affinity, will come as a function of the radius. Understand the basic or the meaning of ionization energy and electron affinity, then you can make an educated choice, okay? Figuring out what happens with all of the properties. Okay, so with that being said, now it's a good time to move on to the next chapter of our journey here. Okay. Okay, so now it's a good point for us to move on to chapter number 8. Uh, chapter number 8 will talk about chemical bonds, and that's what I don't like about this book, because it follows a weird order. For me, this chapter should be before chapter number 3, at least, but it is what it is. I cannot change much about that. So we will talk again about chemical bonds. We already started talking about ionic bonds. So you need to remember what was taught already. And for this chapter, we will cover deeply the covalent bonds. So this is what we need to cover in this chapter. So we will focus on the covalent bonds, starting with Lewis structures and formal charge. So we are going to learn how to connect atoms using covalent bonds. I will talk about expansion of the octet, and then polarity of chemical bonds, length, strength of covalent bonds, and if we get time, cover a little bit of resonance. Okay, so and this is the point that I will take a short break here and reinforce some things that we need to change attitude. So starting here, it is your responsibility to read the book, okay? So for this class, it's a very dense class. I have to cover a lot. 3 hours per week is not enough. This class should have at least 4 hours per week, at least. But again, I cannot change anything about that. I will put a lot of the load on your back. And I've never lied about that. If I'm doing that, it's because I believe you can do it. Okay? I'm not going to force you to do things. It has to come from you. Okay? There is a lot of help out there. There is SI instructor. There is a tutor just for this class. I have office hours twice a week that I stay here. I sit for 1 hour looking at my computer. Nobody shows up. So if you don't look for help, I cannot do anything about that. Remember that you are a small percentage of the population. So you need to be able to do the work that most of the population cannot do it. Memorizing concepts, it is a great start. It will take you all the way to some point. However, there is a huge difference between memorizing and understanding the concept, okay? Understanding the concept, it will take you to the extra mile. Yes. So again, you need to be able to understand things. Let's see if I have something else to say. I think that's it. All right. So again, you have to be able to solve problems. That's the idea of the college, is to train you to solve problems. Because in the future, people will hire you not to do everything that everybody knows. So you don't need a college degree for that. You need to be the one that's capable of solving problems. Okay, so let's recap a little bit about the chemical bonds. So remember that most of the compounds in nature are found as combination of different elements. For example, potassium by itself is highly unstable and reacts violently with water, while salts such as potassium carbonate or potassium chloride are extremely stable compounds. Therefore, the elements will find a way to combine with other elements to achieve stability. Different compounds are grouped in classes as a function of their bonding. And we will cover two major classes, ionic and covalent. Remember that achieving chemical stability means imitating the electron configuration of the noble gases. All the noble gases have one thing in common, which is a full valence shell with 8 electrons. Therefore, the name octet rule. Any element will lose or gain electrons to acquire the stable noble gas electronic configuration, which means 8 electrons in the valence shell. Therefore, the dream of any atom is to achieve 8 electrons in the valence shell. And therefore, the atoms will combine with other elements or with themselves to achieve the stability. There is one exception to the octet rule, which is the duet rule. Some atoms will try to imitate helium, where only 2 electrons in the very first shell is enough to achieve stability. And this rule is called duet rule. And few elements will be able to do that. Those elements are hydrogen, lithium, and beryllium. Okay, for those elements, 2 electrons in the very first shell is enough to achieve stability. Once more shells added, you must have 8. Okay, so therefore, there are 2 ways for the elements to combine. The first one is through an ionic bonding, and the second one is through a covalent bond, forming covalent compounds, also called molecular compounds. Let's do here a quick recap regarding ionic bonding. in the ionic bonding, there is one element that will lose electrons and another element that will gain electrons. So therefore, any ionic compound is formed by a cation and an anion. For example, here, sodium, 11 electrons in the valence shell, belongs to the group 1. So we know that there is 1 electron in the valence shell, and chlorine belongs to the group 17, therefore 7 electrons in the valence shell. To achieve stability, sodium has to lose 1 electron, so therefore achieving the octet here, and chlorine has to gain 1 electron. So therefore, sodium and chlorine will combine to form sodium chloride, very stable compound, 1 cation, 1 anion. Therefore, this is an ionic bonding. Another thing about this course is that you cannot compartmentalize the concepts. At some point, they will show up again. So you have to have a big picture of everything. Everything you learn will be used at some point in the future. Okay, so let's talk about the characteristics of ionic compounds. Okay, when sodium and chlorine combine, they will form this very well organized crystal where we have sodium surrounded by chloride ions. See here that sodium is the small sphere and chloride is the large ones. That's because sodium plus lost 1 electron, therefore the radius decrease, and chloride gained 1 electrons, therefore the radius increased. Characteristics of ionic compounds involves a cation and an anion. The compounds are crystalline, meaning that they have a very well organized structure in the solid state. Because we have a cation and an anion, there is strong electrostatic interactions between the ions present, okay? And this interaction between a positive and negative charge is the strongest one that you can have that will reflect in high melting point and high boiling point as well. Usually formed between elements from groups 1, 2, or 13, which are cations, and elements from groups 15, 16, or 17, which are anions. And although the interaction is strong in ionic compounds, they are very brittle, meaning that a small pressure on the surface of the solid will easily crack the solid. So let's see the reason why you can easily break an ionic solid. Okay, so let's look here at uh, an ionic solid. If we were able to see the atoms forming the structure, we would have an ion, the negative charge here, then the cation, the positive charge, and they will alternate uh, in all the directions. Okay, so negative, positive, positive, and going down, positive, and negative. See that each layer is alternated regarding the charges. When we apply a pressure on the surface of the solid, what we are doing is shifting one layer of the solid. So it was leveled up. So we had here a negative and a positive. Now we are going to shift one layer down, for example. So now what happens is that we are facing negative charge with negative charge, positive charge with positive charge, and the same here, negative with negative, the next layer positive and positive. So we know that charges with the same sign, they repel each other. So right now here we have a lot of repulsion between the unchanged layer and the changed layer, and that will cause one of the layers to disconnect from the solid structure. That's the reason why it's very easy to break an ionic solid. The smallest pressure will shift the layer, cause repulsion, and then break apart the solid. And that's the reason why ionic solids are brittle. All right, so now it's a good point to shift our attention to covalent bonding. Hydrogen, oxygen, and nitrogen are found in nature as gases that have molecular formula H2, O2, and N2, respectively. What is the kind of bond in this compound? If we look at hydrogen, we have only one electron in the valence shell. Therefore, to achieve stability, hydrogen needs to get one electron. Looking at oxygen, now we have 6 in the valence shell right here. Therefore, we need to combine with other elements to get 2 electrons. And nitrogen, 5 electrons in the valence shell. Therefore, we need to get 3 electrons to achieve stability. Somehow, hydrogen combines with another atom of hydrogen and forms a stable compound. Oxygen can do the same thing, combine with another atom of oxygen and achieve stability, and nitrogen as well, combining with another atom of nitrogen and achieving stability. How is the bond in these compounds? How is that possible to combine with itself and achieve stability? So that's what we are going to tackle regarding covalent compounds. Covalent compounds are compounds where there is sharing of electrons So biggest difference from the ionic bonding where there was donation of electrons. In this case, nobody will lose and nobody will completely gain electrons, but we are going to share what we have to achieve stability. The compounds are crystalline. Because we are not forming charges, there is weak interaction between the atoms present that reflects in low melting point and low boiling point. Covalent compounds are usually formed between elements from groups 13, 14, 15, 16, 17, 18, and hydrogen. Okay, so elements from groups that need to get electrons to achieve stability. Okay, very good. So the way the elements will combine in a covalent bonding uh, will be through the formation of basically three different kinds of bond. So let me quickly change to my other screen, then I can make some notes here. Okay, so when we have only one pair of electrons being shared, we call this a single bonding. And that's what happens when a hydrogen combines to another atom of hydrogen, okay? Showing right here. So in this case, we are going to represent the number of valence electrons by A dot. One atom of hydrogen has one valence electron. Another atom of hydrogen also has one. They will combine with each other. And when the electron is shared, I'm going to put this line around the number of electrons being shared. If we have two electrons or one pair being shared, that is called single bond, and we can represent that by a trace. Okay, so the representation on the left and on the right, they mean the same thing. So now we have two electrons being shared. That means the two electrons belong to the two hydrogens, okay? So when electrons are being shared, they belong to the whole molecule. Well, that solves the problem. Hydrogen needs to get two electrons to imitate the helium. Now, combining with another atom of hydrogen, the two electrons are being shared, therefore they belong to both atoms involved in the bonding. Another way to share electrons is through a double bond. So that's what's going to happen with oxygen. So oxygen has 6 electrons in its valence shell. I'm going to represent 2 of the electrons here. So therefore needs to get 2 electrons. So they are going to share the first pair and then share the second pair. Now we have 4 electrons or 2 pairs being shared. That's called double bond. And we can represent that by 1, 2 traces. Remember that the electrons being shared, they belong to both elements involved in the bonding. Okay, so it's like each oxygen got the 2 electrons that were missing. And for nitrogen, we know that each atom needs to get 3 electrons. Therefore, they will connect with each other, sharing 6 electrons or 3 pairs of electrons. Okay, 1, 2, and 3. And that's called triple bond. We can represent a triple bond by 1, 2, 3 traces. Again, each pair being shared belongs to both atoms involved in the bond. Okay, so I started talking about how to represent the electrons using dots, and that's called Lewis notation. So let's show you a more complete Lewis notation and how we do that. So when we use the Lewis notation, we are going to represent only the valence electrons by dots around the element symbol. Okay, so what matters for us when doing a chemical bond are only the valence electrons, because those are the most exposed and the reactions will happen in the valence shell. So let me give you 2 examples here on how to draw the Lewis notation. Let's start with carbon. Carbon belongs to the group 14. Therefore, every time we are in the group 13, 14, 15, 16, 17, or 18, if we want to know the number of valence electrons, we have to subtract 10 from the group number. So therefore, 14 minus 10, that means carbon has 4 electrons in the valence shell. To draw the Lewis representation of carbon, we are going to draw the symbol of the element and distribute the electrons in the valence shell as dots around the element. Okay, so it doesn't matter the order that you follow here. You must have 1, 2, 3, and 4 dots around the carbon. This symbol shows you that we have 4 electrons in the valence shell for carbon. Of course, this is not a stable structure. We need to get 8 electrons in the valence shell, so carbon will combine with other elements to achieve that. We can do the same thing for oxygen. Oxygen belongs to the group 16. Therefore, 16 minus 10, that's 6 electrons in the valence shell. Lewis representation for the oxygen. First comes the symbol of the atom. And now we are going to distribute 6 electrons around the oxygen. 1, 2, 3, 4. Doesn't matter how you go with the 5th and the 6th. I'm going to go like that. The important thing is that you need to show that there are 6 dots around the oxygen atom. Each dot represents one of the electrons in the valence shell. Okay? So that's how we use the Lewis representation or the Lewis notation for the elements. And that's a very useful representation that we are going to use to build the covalent compounds, okay, to connect atoms using the covalent bonds. Right. Let me shift back to the PowerPoint. Okay, I showed you how to use the Lewis notation to represent the valence electrons for any element. Okay, so in here is just the same thing that I showed you. So we are going to represent the number of valence electrons as a dot. Group 1, just 1 electron. Group 2, 2 electrons. And we jump to the group 13, where there are 3. I showed you for carbon and oxygen and so on. So you can use the same concept to represent anything you want. All right, come on, guys, let's do it. You can do it. I believe you can do it. Show me that there is still a heart pulsing in your chest there and you are not just like a zombie watching a video, okay? So with that, I think that's more than enough for today. So I will stop at this point, and then on Friday, I will show you how to connect atoms using the covalent bonds, okay? So have a good rest of your day, and I will see you on Friday.
Bye. Thank you.
Have a good day.
Bye.
Bye.